before the exam. So we are on resistance and powering. And resistance is covered by here. Right. And then we will do power estimation today. So once again, two major components, frictional and residual. So frictional comes from viscosity. Residual comes from wave making and also pressure difference around the surface. But wave making is more bigger than, especially in high speed, wave making is dominant. So for the fast ships, wave making is the most important part for the Navy ships, especially. And smooth hull surface, usually the ship hull surface is smooth, free from surface, or C2 curve, C2 surface, C2 continuity, and minimize frictional resistance, but still there. So good hull form, as a designer, you should design a good hull form to make minimize residual resistance too. Not only frictional resistance, residual resistance is depending on the shape, hull form, rather than the frictional resistance is depending on the area of surface. Anyway, in most ships, frictional resistance is 3 or 4 times large as residual resistance. That is not true, actually. It depending on the speed and also the Reynolds number. So as I told you that high-speed vessel like frigate of Navy, wave-making resistance is bigger. So this one should be modified anyway. In most slow ships, you can say slow ships. All right. And here, high-speed ships, two resistance might be about equal, but depending on speed, sometimes wave making is bigger. All right, so here is the video. Let's see this. The propulsion coming from.
Get a real-time bird's-eye view of your projects. Create project plans.
CRISO is a nearby research institute in this town. Efficiency improvement and all this.
International Maritime Organization has mandated adoption of the Energy Efficiency Design Index for all vessels contracted since 2013. IMO also resolved to reduce the noise generated by a ship to 3 decibels within 10 years and to 10 decibels within 30 years to conserve marine mammals and fish. Accordingly, the global shipbuilding industry is making all-out efforts to improve the propulsion efficiency and protect the marine environment. Dr. Hanshin Seol's team at Korea Research Institute of Ships and Ocean Engineering has world-class technologies in this field. Based on systematic researches on improvement of propulsion efficiency and noise reduction, Dr. Seol's team developed innovative technologies that are indispensable for development of eco-friendly ships. Only 70% of the power of ship propeller is used for propulsion, and the rest disappears due to friction, heat loss, vortex, and so on. In order to increase the propulsion efficiency of the ship, it is necessary to minimize the loss by improving the design technique of the propeller and developing the high-efficiency propeller appendages. Various types of strong cavitation occur in the propeller. This is the main cause of noise and vibration of ship, loss of propulsion efficiency, and propeller and rudder erosion. Dr. Sol's team has managed to not only enhance propulsion efficiency, but reduce radiated noise using a technology that improves the propeller cavitation. The existing ship propeller hub has a round cup-shaped cover. Its sleek shape, contrary to expectations, creates strong vortex flow and forms a strong hub vortex cavitation. In an attempt to inhibit the formation of vortex, the team developed a new propeller cap in a different shape called K-cap. It can improve the propulsion efficiency while efficiently inhibiting formation of hub vortex cavitation. K-cap and fin is a combination of K-cap and a simple shaped plate.
Okay, that's enough for today. Any question? So this one is more on propeller design rather than resistance. So that's why I stopped the video. But if you have interest, you can see more. So what happened to energy used by the fuel? So not all the energy that goes into the propeller shaft, which is the propeller. There is a loss. So fuel energy, there is 100%. There goes 30% goes to exhaust gas as heat gas, and then cooling system 27%. So remaining is only 40% is used by propulsion, but also there is a frictional resistance in bearing and shaft loss, and propeller loss is also 15%. So that only 24% of fuel energy is used for the propulsion. So small fraction to overcome friction, bearing, seals. Seals is used for water coming into the ship. Finally, the propeller converts the torsional energy into thrust, pushing energy, translational. Torsional to translational energy. There is a engine. These three engines is only for electricity generation, but these bigger two engine is the main engine. So they can be propelling two propellers, and there is a gear box so that they can change the RPM of propeller. So power definition, there is effective power, thrust power, delivered power, shaft power, brake power. There are so many different numbers there. So effective power is far behind, so that they are used for propelling the ship or against the resistance of the ship. Once you remember that you swimming, or as you learn swimming, or you can think about running inside water, jogging or running or marathon. Running is much harder than running inside the air because of the water, right? That's the same as a ship or fish. So effective power is used for against the resistance of the water. And then thrust power is just behind the propeller, and delivered power is just before the propeller. So there is a loss or conversion of delivered power to thrust power by the propeller. So they are saying about 50% is lost by propeller itself. And then shaft power is before the shaft, there is a stun pipe or pipe, there is a bearing or sealing, so that they lose also energy due to the sealing and bearing. And brake power is just after the engine. So brake power is the biggest among these powers. And then there is a gearbox. So there is loss, gear efficiency, and bearing efficiency, and shaft efficiency, shaft sealing efficiency, and then propeller efficiency. So there are so many efficiencies. And there are definitions of what is meant by these numbers or equation powers. So power definition, effective power in the car motor, not wave. Car motor means not real motion, very stable motor. Power required to move the ship at a given speed. There is no propeller action. Thrust power is the power produced by the propeller. Delivered power is power delivered to the propeller. So before the propeller. This thrust is after the propeller. And shaft power and brake power. So as I told you that each effective horsepower is smallest in number. Brake power is just behind the engine, so it is biggest. And there is a losses because of the efficiency. And how can you estimate power? So as a designer, you need to estimate power. That's why, because you need to choose the engine. And engine selection is important part of designer. And if you choose a smaller engine, then the ship cannot have the required speed when constructed. So it is a failure to as an engineer or designer. If you choose a too big engine, then it can cost much. So it is a loss to the shipbuilding company. Also, the bigger engine has a bigger size and volume, so that the engine room arrangement is difficult to arrange it, to host that bigger engine. So as a designer, you need to find the optimal size of the engine, or minimal size is best to meet until as long as you meet the speed guarantee. So it's not easy. Anyway, effective horsepower is most important for the speed, and there is a propulsive efficiency between PE and PD, and the propulsive efficiency is made of 3 parts: H and O and R. So this is an important portion of propulsion or propeller. So we call H as a hull efficiency, O is a propeller efficiency, and R is a relative rotative efficiency. So hull efficiency is coming because of the wake, and also there is a thrust deduction. The speed of water is different near the propeller. That we call this is a speed difference, gives you a thrust deduction. And wake gain is coming from wake is speed distribution around the stern area. So that gives you additional power because of the speed and other things. And open water propeller efficiency, that means a propeller without hull, without ship. The propeller is designed and tested in an open water without any ship, not behind the ship. So we call this is an open water propeller efficiency. And relative rotative efficiency is more complicated. There is a explanation behind. The ratio between the effective horsepower and the thrust horsepower is propulsive efficiency. And wake, W is wake fraction, W, wake fraction, wake gain, and thrust deduction. There's another coefficient. So how can you select engine? So now you need to estimate frictional horsepower, frictional resistance, and motion in viscous fluid. And then you need to estimate wave making horsepower, wave making resistance. That should be used for create wave. Okay. To the wave system created on the surface. On the surface of the motor. And then, so by using frictional resistance and wave making resistance, also eddy resistance, you can get the total resistance and power requirement for appendage, that is we call eddy resistance. So 3 part gives you a total resistance. The sum of over mentioned resistances will give you the effective horsepower. So total resistance is the same as effective horsepower. Then you need to compare the delivered horsepower because of the shaft loss and propeller loss, and finally get to the brake horsepower. So that you can get the engine power from brake horsepower. This is almost same as engine power, brake horsepower. And then you need to additional margin. That margin is for C margin, we call that, because there is a C has a wave and wind and current. So there is a bad weather and good weather. So you need to have by experience, you usually have a 20% additional margin. And then you can get select an engine from the engine maker's brochure or turbine. So diesel engine using the engine manufacturer's catalog. For the submarine, deeply immersed body moving at constant speed, there is no free surface. Okay? So there is no wave making resistance. No wave making. So ideal flow, if there is no viscosity, there is no resistance. So this is something special. We call this a D'Alembert paradox. But it is not true for the real ship. I mean, this is a velocity because of the shape. So there is a streamline is more condensed. The speed is higher here. So the pressure is low. So at the stagnation point here, at the pinpoint, there is a pressure is higher at the tip and the tip end. So it is shape of flow around the submarine. And for the surface ship, the ordinary ship, there's a vortex cavitation. Vortex cavitation, there's a question coming deep. Cavitation, can I say, it is something like a boiling, right? Boiling. If you boil water, there is a bubble is coming from the surface, bottom surface of the plate. And that bubble we call as cavity. Right? But cavitation phenomena is coming when the pressure is fluctuating. So you know that when we go up to the high hill, the highest mountain in Everest in near India, you know that the boiling temperature is lower than 100 Celsius because the pressure in high mountain is lower than here in our place. So that you know that the water boils in lower pressure when the when pressure is low. Right? So around the when propeller is rotating, the flow around the propeller stream, we call this is a wake field. And that wake field, around the wake field, the pressure distribution is different because of the ship in front of the propeller. That gives you a fluctuation of pressure on the surface of propeller when propeller is rotating. So when the speed is high and also pressure is fluctuating, the cavity is formed someplace and then collapse and form, then collapse and form, then collapse regularly, periodically. So we call this is a cavitation phenomenon. We'll see more in propulsion and in later stage of this class. So I will explain a little bit more on cavitation. And vortex is vorticity. Vorticity is a rotating water. Vortex. Okay. And ship moving on the water surface, there is a resistance force coming from similar to submerged body. That is a viscous resistance. But in addition, there is a free surface. Free surface means a surface between air and water. There is a wave making resistance. And so wave making energy is lost. So we call this as a Kelvin wave, as we see from the previous lecture. And so again, the friction in the shaft bearing and the seal, shaft bearing and seal, right? Shaft bearing and seal, that can give you a 1 or 2% loss. Very small number, but this is big because the engine is big. And propellers convert torsional energy into thrust, translational energy. It is usually 70% efficiency. It is a good propeller design, 70%. And there is a propeller hull interaction because of the ship hull. The propeller has difficulty because of the flow speed is different around the circle of the propeller. But the propeller is rotating. So wake gain, the propeller operates within the relatively slow moving water comparing to the outside water or speed of the ship. Here, because of the wake or behind the hull, the average speed of the water is slower. So we call it slow moving water, which gives you some advantage, regaining. So we call this as wake gain. And thrust reduction, the propeller reduces the water pressure on the stern. Right, pressure on the surface of the ship because of propeller is suctioning the water. So pressure on the surface, hull surface in the stern area is lower than the other places. So there is a energy loss because the pressure induced the suction. Anyway, so how can we estimate horsepower? As I told you before, we collect all the resistances. Then it can be total resistance can be horsepower. But it is not easy. Challenging responsibility of naval architecture is selecting an engine that will drive a proposed ship at the guaranteed speed. It is most important. It is contract signed when ship is contract purchased. There should be a guaranteed speed. So it is very important. Horsepower. Horsepower, you already know that. Force multiplied by speed. And metric horsepower, there is about 735 watt. And engine output is brake horsepower, shaft horsepower, already know this. Because of diesel or gasoline engine, we usually saying bhp. But steam turbine, we usually calling as a shaft horsepower, but it's not important. But anyway, it is identical in a direct drive diesel engine. What is direct drive diesel engine is there is no gearbox. So in big ships, the engine itself is very slow RPM, around 100 and 150. Can you say somebody, one of you, that for my car, when I'm driving, what is the average RPM of the engine? Can some of you answer this? What is the average normal riding car? What is the average RPM of the engine of your car?
2000.
Louder?
2000.
2000? Yeah, 2000 or 3000. That is a normal range of RPM of my car when I'm driving. Right? But here, as I told you, that large diesel engine in ship of horsepower of 50,000, they are rotating in 150 RPM, not 2000. Very slow, right? And in that case, they can use the propeller direct to the engine shaft. So no gearbox. If you have a 2000 RPM of engine for the gasoline, you need to have a gearbox to lower down the propeller speed. So they call this is a direct drive. Right, 800 when it is idling. Yeah, it's car engine. Yeah. Idling means not at the parking place. Parking place, the engine is idling, but it still has an RPM of 800. All right, let's get back to the. So, direct drive diesel engine means there is no gearbox. Right. Marine engine market. Global marine engine market size is $1 billion. In 12 billion, or it will be 70 billion in 2026. And market share of engine by ship type is bulk carrier is 40%. And Asia Pacific marine engine market size is 5 billion. So it's 1/3 or more than 1/3, right? Among 12 billion, 5 billion is consumed in Asia Pacific region, because there are big shipbuilding companies in China, Korea, and Japan. Okay. Question? No question. All right. And we can move on to second part, or have a short rest. Or we can go on to next part. Okay, then so this is the third part of the resistance sampling. So we are in chapter 8, and I will cover at this slide that about model test, and dimensional analysis and ship resistance prediction. So how can, as a designer, how can you predict the ship resistance based on ship design lines and also guarantee speed? And finally, you need to select a propeller and in the section of propulsion. So model Bayesian theory. So prediction of ship speed is very important as a designer, naval architecture, because you need to have a guarantee of speed. It is commercial contract, but if you think about the Navy ships, speed also important, probably more important than commercial ships, because speed is important for winning the battle against enemy ship, especially in old days. Not anymore in these days because of the missile and high-speed electronic attacks, torpedo, something. They are more faster than ships, so ship speed is not so important as much as in the old days. But still, if you think about as a Korean student, that there is a problem between China fishing boat coming to the Korean water to catch illegally the fishes, so that the police, ocean police, marine police, Coast Guard, we can say, Coast Guard need to have a faster ship than the ship of China illegal fishing boat. In that case, ship speed is important. Anyway, so as a designer, you need to have a prediction problem. So in old days, they have a model test. But it was until 1868, about 150 years ago, the William Freud of UK, not America, United States. Freud. So Freud number is coming from his name, Freud number. And he sees that there are two major resistance components. But he found that they follow different physical laws. So model test should have a scale down from the model ship. A real ship has bigger than a model ship. So scale effect is important. But he found that it does not, the two components does not follow the same physical law. So that he create a Freud number, and the other one is the Reynolds number, cannot be matched at the same time. So I have experience of wind power model test. Some of you are staying in Eureka building where I am located. At the floor entrance, there is a small, not small, wind power model is rotating in this building. I need to have a picture of him. But anyway, so we do, that is a model of a floating wind power system. So we did design and also tested them in ocean or model Bayesian. But the problem is we tested two purposes. One is because it is floating wind power, it is something like ocean plant, and in the wave, what is the motion of that wind power system, floating wind power system? The other one is power generation by wind. But still, we have a problem with when we measure motion of the system in wave, we follow the Froude number scale. But the propeller wind power generation is follow the Reynolds number scale. So we cannot match both of them together with the same model. So that is a similar problem as this. So friction, so the William Froude found that kind of problem at the time, 150 years ago, and he treated friction resistance and wave making resistance separately based on laws of similitude, and similitude is coming from dimensional analysis. So the scale effect is important, and different physical characteristics coming. Anyway, this is the Navy, UK Navy test tank in 150 years ago. And William Froude developed this kind of system at the time. And dimensional analysis. So what is dimensional analysis? I guess you already learned about this, but probably it was not easy to understand. So I just remind you, I will not explain fully. This is a functional relationship between a set of non-dimensional groups of dimensions. The primary dimensions in mechanics can be mass, length, and time. So for example, there is a pendulum case. So in the drawing, right-hand side, there is a physical quantities of m mass, length of the pendulum, and g is a gravity acceleration. Right. So time is coming with the g. So the t is what is it? Time of travel, a period. Right? So it is something like a watch, pendulum watch. So the period of clock is important to measure the time. And then if you have a shorter pendulum, the period is short, right? And long pendulum gives you a long period of cycle. So depending on the mass, also length and gravity is the same, g, period is fixed. So anyway, the primary dimension here in mechanics is mass, length, and time. So oscillatory motion, again, natural frequency of the pendulum, right? We already see many times. The frequency is calculated by using length and g. Okay? So length is most important. The frequency is reverse square root of reverse of length scale. Once again, I say that length is longer, the frequency, the period time clock is longer, speed is longer, right? Traveling cycle. That means frequency is lower, t is higher, right? So length and frequency and period is in reverse way. And dimensional analysis is very similar to this kind of drawings. So by calculating, multiplying, and dividing, we know that only the remaining part is yellow triangle, and also second number, second equation. The remaining part is something like this. In question of 3, then we know that orange bar is remaining. And for the number 4, we need to have a double circle, right? Or donuts need to be there, please. That kind of thing is dimensional analysis related. So applying dimensional analysis to sheet resistance, the Fluid did this kind of. And he found that resistance of the ship depending on following physical quantities of density, speed, length, and viscosity, gravity, acceleration, and pressure. So there are 6 variables, but density, viscosity, G, gravity is constant almost. So that the remaining part is speed and length and pressure. Pressure may be a little bit fluctuating, but we can assume as sometimes it can be a constant. Sometimes it can be used as a variable. But anyway, a big variable is V and length, V and L, length and speed, and resistance. Fluid make a hypothesis that dynamic similitude, not static similitude, for both friction and wave making cannot satisfied at the same time. So it should be separated out. So practical method is to deal with frictional resistance and wave making resistance separately. So he made an equation. So total resistance coefficient CT is made of CR and CF. So frictional resistance is separated out from the other resistance remaining or residual resistance because of the dynamic similitude. So the resistance is further divided into 4 parts. One of them is frictional resistance, so it can be separated out. The other 3 can be wave making and eddy, but together we call this is a residual. So at the bottom there is a box. Residual resistance is made of wave making resistance and eddy resistance. And the remaining part is air resistance, but this is very small portion comparing to the other 3 portions. So we can use this additional small contribution. So the major part is to estimating frictional resistance, wave making resistance, and eddy resistance. And later 2 parts, wave making and eddy is coming to residual as Fluid assumed in 150 years ago. So he found this a Fluid number made of this dimensional analysis and dynamic similitude. He found this kind of a relationship between resistance and S is a surface area of wetted surface area and speed. So ship of different size means a model sheet and full size sheet has a different size. We'll have the same resistor resistance, CR. That is interesting, right? So CR is independent of size. If they are moving at the same value of the Fluid number. So the model test, the speed of ship is different from the full ship speed, the guaranteed speed. But anyway, we can calculate the speed of model test by using Fluid number. If we make this speed correspondence, then we can get the CR from the model test. That is the very good idea. So such a speed, we call this as corresponding speed. And the parameter is called the Fluid number or symbol of Fn. So that is the story, how the Fluid number is formulated in 150 years ago because of the ship resistance estimation at the time. At the time, it was a very difficult problem. Nobody can answer this. And William Fluid developed such a theory at the time. So he was a very good engineer. All right, so there is a fluid mechanics. You see that laminar flow and turbulent flow. And in between, there is a jump between them, or you can say separation. So laminar flow is very slow and calm, and it comes with a separation. There is a turbulences. An eddy or vortex is coming inside the turbulent flow, rotating part. There is no rotating part in laminar flow, right? Once there is a separation and turbulence, there are so many rotating part of vortex and eddy. So Reynolds number is coming to the turbulent flow mostly, not laminar flow. Anyway, for a deeply submerged body, the frictional resistance is dominant because there is no wave resistance. Frictional resistance coefficient F will be the same for the model and ship, provided if the parameter Reynolds number is the same. So that is another interesting finding. So we call this is a Reynolds number. So if you have the same Reynolds number, you can calculate CF by using model test, but separate model, not Froude number. Here is a Reynolds number model test. So two different model tests, you can get CF and CR. Then combining them, you can get total resistance coefficient, CT. So come back to this calculation that Froude hypothesis. CT can be divided into CR and CF by doing different model tests. CF for Reynolds number testing, same Reynolds number. CR for the same Froude number. You can get the number coming from model test, two different model tests. But anyway, if you get the CR and CF, then you can get CT. Then you can calculate the resistance of the ship by using this equation. This is only for frictional equation. Oh, here's a residual equation. Oh, there's no equation, but the equation is the same, right? Only R equals C. Okay, so by using model test result, somehow you can calculate ship rate, total resistance. How? We follow the numbers. So model test. Model is made to a linear scale ratio of lambda. Lambda is a length difference ratio between real ship and model ship. So in this building, the Eureka building, at the entrance, I showed you the picture in previous classes that there are two model, real model, wood model. It is used for real model test. One is coming from Samsung company, the other one is coming from STX company. And usually they use a scale ratio of 20. So in this building, the model is about, say, how long is it? 10 or less than 10, so 8 meter something, or 10 meter, you can say. Then 20 times of scale, then real ship can be 200 meters. Right? So scale ratio of that kind of model test is 20. But for the floating wind power, I told you before, that was scaling factor of 6 something, 6. We try to make as large as possible. But if you make a bigger model, the similitude or correspondence or relationship is much, you can get more correct solution. but the problem is you cannot test because the model basin, the towing tank cannot accommodate the big model. And also it costs much if you make a bigger test models. Right? The two problems. The main problem is size of the model basin, the pool. Anyway, so we will learn over a range of corresponding speed used by fluid number or the corresponding speed. So you can get total model resistance measured by separating out CF and CR. So corresponding speed is for CR, but frictional resistance of the model is calculated assuming the resistance to be the same as that of a smooth flat surface, has the same length and relative surface area as the model. Right? See that the surface area of the ship, and here they are saying wetted surface area of the model, scaled down model, is same as the frictional resistance of the flat surface, flat plate, but that should have the same area and also same length and also same Reynolds number. So by testing the flat plate of this condition, then you can calculate frictional resistance coefficient. Right? The residual resistance of the model is found by subtraction of model test total measured. This one is measured by towing tank test, and frictional resistance is subtracted because we want to have a model residual. This is force resistance, and using this one can calculate the CR. Not this is total resistance of the model, but CT is a coefficient. The residual resistance of the ship is calculated as from the model residual resistance. You can calculate full ship resistance, residual resistance by cubic of scalation. And as a separate out, the frictional resistance is calculated using a frictional coefficient chart. Because it is based on area, length, and Reynolds number, you can get many tests already with flat plate, and then has a chart of different cases. So you don't need to have a test of a flat plate again. You can use only chart to find out the frictional surface resistance. So that you need to have a two model test. You need only one model test to get the residual resistance coefficient. So total ship resistance is calculated by frictional resistance coming from chart and residual resistance coming from model test. And the power requirement EHP, effective horsepower, is calculated by resistance multiplied by speed. Right? It's a little bit complicated. Do you have any question? Can you follow this reasoning? Otherwise, you need to raise a question. All right, so we may have a short break, and then we finish up this slide set. Probably that can be the end of this class. So we're still remaining at the other part for the Thursday class. All right, so 2 minutes. I'll be back at 2 o'clock.